Hi everybody and welcome back to Geology 311, Stratigraphy and Basin Analysis. For week 6 lectures, we're going to be looking at chapter 7 in the Brookfield text, which is the time dimension. We've already covered vertical and horizontal dimensions, and now we want to look at it from a time context. So some of the breakdown of some of the units in the Brookfield text that we'll be covering involves age equivalences, looking at relative age dates. Actually going to throw in some biostratigraphy into that as well. Sorry, can't resist. And also then looking at numerical methods and how we calibrate our geologic timescale with radiometric dates. So let's jump right in. Over the last few centuries, there's been a number of ways in which scientists and researchers have attempted to figure out the age of the Earth. Really, the earliest of these recorded attempts was Archbishop Usher, who in the late 1650s attempted to date the age of the Earth using kind of backtracking biblical transcription. And based on his work, he estimated the Earth to being 4004 BC for its origin. Notably, though, he actually was able to nail it down to a date, to which it's October 26, 4004 BC, which is also appropriately my birthday. Of course, I'm not that old, and this is a really inaccurate way of gauging the age of the Earth because it's not scientifically testable. So Usher, while he was, I guess, a great archbishop, not really the best at estimating the age of the Earth. Similar, and not to be confused with the R&B recording sensation Usher, who is also, as far as my knowledge, not very good at dating the age of the Earth. However, in the late early 1800s, George Buffon had a slightly different approach for trying to figure out the age of the Earth. He took spheres of iron and would heat them up almost to the point of melting and then measured how long they took to cool, thinking that since the Earth has a significant portion of iron in its subsurface, that he could get an estimate for the age of the Earth this way. Unfortunately, Buffon's method was not a very good timekeeper. And of course, this is not to be confused with Gianluigi Buffon, the Italian goalkeeper, who also has nothing to do with geology. In the 1850s, Helmholtz and Kelvin, that is Lord Kelvin, attempted to date the Earth using their solar contraction hypothesis, which deals with the thermodynamics of heat loss of the Earth, the Sun, and stars. Not to be, of course, confused with Kelvin Fletcher, the British actor and race car driving superstar. In the early 1900s, Irish physicist and geologist John Joly tried to date the Earth looking at the rate of salt accumulation in the oceans, though not taking into consideration unconformities and inconsistencies in evaporites and other sedimentation. This, of course, is not to be confused with Angelina Jolie's movie Salt, which has unfortunately nothing to do with sedimentology. Although contemporaneous with John Joly was Boltwood and Rutherford's work and on the first radioactive dating of rocks, starting to approach our more modern estimates. Now, Rutherford is not to be confused with Mike Rutherford, the guitar and bass player for the progressive rock band Genesis, though his guitar licks have sometimes been described as nuclear. Now, something that is important to note on this diagram is with each progressive attempt at dating the Earth, standing on the shoulders of the previous researchers and learning how they got things wrong, we started to get closer to the actual correct answer. So we know that averaging estimates of sedimentation and salt doesn't really work. Helmholtz and Kelvin didn't take radioactivity into consideration. Buffon also didn't realize that the composition of the Earth's various portions, core, mantle, and crust, are of different compositions. Usher's method is not testable. However, when we start getting towards our modern methods, with especially Rutherford and Boltwood's work on radioactivity, we started finding a timekeeping device in the form of isotopes, a clock that doesn't easily reset. So I think it's important to note that throughout time, why I like this graphic image right here, is that it shows how with each progressive attempt to date the Earth, we got closer and closer. Notice none of the next attempts took things back in the wrong direction. But in reality, getting an absolute age for the origin of the Earth is great, but there's a lot more to it than just that. That's just a number. To really understand the order of events, we have to look at relative age dating and separate it a bit from absolute age dating. And we've covered some of this already in the semester, but I want to put it in this context, that relative age dating is determined through our stratigraphic methods. And absolute age dating, while very important, is really just kind of numbers that we can hang on those stratigraphic events. Now, sometimes when we have multiple stratigraphic events that are datable, that can give us ideas about rates of some of these geological phenomena. And so what I want to do is talk a little bit about relative age dating, and then at the end, we'll end with some of our absolute techniques. Of course, to do this, I also want to remind everybody of the bane of their existence, the differences between geochronologic and chronostratigraphic units. Again, I know we covered this on the exam, but these will keep coming back to bite us. Chronostratigraphic units like ionothems, erythems, system series stages, and chronozones, these are all based on rocks in a time context. So for example, the fundamental unit you'll remember is the system of a chronostratigraphic unit. And this is all of the geological materials we have that represent the abstract geochronologic unit of a period. So geochronologic units, when we give them a number to start and end them, those are based on absolute methods. However, we wouldn't really know that we had a geologic period if it wasn't for the chronostratigraphic system. And these are based on the physical relationships of correlation that we discussed last week for our relative age dating. So in the three stratigraphic columns you have here, we have column A, which is a shale capped with a limestone, capped with another shale with a basaltic dike that cuts through two of those lower units. In column B, we have a limestone, the same shale 2 that we had from column A, and the same sandstone from column 1, or column A. And then in column C, we have a limestone at the bottom, shale 1, which is equivalent to the one we see in column A, and a sandstone from all three units. We can correlate these across using Steno's principles, and hypothetically, we could use absolute age dating techniques to date that basaltic intrusion, which will give us an idea about the time in between shale 2 being deposited and the sandstone deposited before it. Ultimately, all of our stratigraphic methods have yielded our geologic timescale, and you'll notice that this timescale is set up chronostratigraphically with ionothems, erythems, series and subsystems, and series themselves. So again, looking at upper, middle, and lower, we're talking about stacks of Ordovician rocks, for example. Okay. We've been able to put numerical age values on here based on our chemical methods, looking at radiometric isotopes, which we'll talk about here in a little bit. But if we look at our age of our Earth in the form of a, let's say, a 24-hour clock, you can see that most of Earth's history of the 4.5 billion years we have of it, like the first 18 hours of the 24, are essentially the Precambrian. Everything after that would then be the Phanerozoic. And what we're going to be doing later in the semester actually is going through kind of a stratigraphic history of North America, specifically looking at tracing basins over time. But I want to point out that the divisions of our systems and periods, whether you're looking at geochronological or chronostratigraphic perspectives, Cambrian, Ordovician, Silurian, and onward, are not based on stratigraphic events alone, especially lithostratigraphic, but on biostratigraphic events. These are based on fossils. So we're going to talk a little bit about biostratigraphy in this lecture, look at a couple of biostratigraphic techniques and concepts, because we've only skimmed the surface on this a little bit. And later in the semester, we will be doing a lab project on this, but this seems to be as good a place as any to discuss biostratigraphy. So in order to use fossils to help us constrain time in the geologic record, we look at our biostratigraphic methods, which is really how we correlate units based on their fossil content. Now, there's a sub-branch of biostratigraphy that sounds very similar, and this is stratigraphic paleontology. And this is also very useful, but it's a little different. This is looking at the study of fossils and how they're distributed in various geologic formations. So stratigraphic paleontology is much more descriptive, and biostratigraphy is a little bit more applied. So when we look at biostratigraphic methods, it's how we correlate and find equivalence specifically from one unit to another based on fossil content. Stratigraphic paleontology is more looking at the distribution of a taxa or a taxon or numerous taxa throughout the stratigraphic record. So they work together, and sometimes they're grouped and lumped into one big biostratigraphic ball. But I want to just make sure people understand the subtle differences between biostratigraphy and stratigraphic paleontology. Using fossils to tell time, or biochronology, requires first understanding what we call datum events. We have what we call first appearance datum and last appearance datum, or FAD and LAD, respectively. We can see and describe first appearance datum as corresponding to the speciation of a taxon. In other words, the first time it appears in the fossil record, roughly corresponding to its speciation evolutionarily. The last appearance datum more or less corresponds to the extinction. This is when we stop seeing it in the fossil record, thus it stops being prolific. Now, if we have numerous taxa, in this case, we're looking at 4 taxa, A, B, C, and D, we can describe the first appearance of an organism in A, and we can describe the first appearance of an organism with B. And we can see the last appearance of C and the last appearance of D, and depending on our ability to date these rocks, we can actually get some radiometric dates or calculate it based on sedimentation. Notice in this case that we can get a radiometric date for A and a radiometric date for D, but we can calculate the sedimentation rate and thus figure out an age for B and C by applying both absolute and relative age dating techniques. And we'll talk a little bit more about how we use sediment thickness and these calibrated times to yield sedimentation rate here in a moment. Small single-celled organisms that produce small fossils, what we call our nanofossils, like coccolithophores or radiolarians or diatoms or foraminifera, are particularly useful for biostratigraphic work and biochronology. So here we're looking at zones of a number of different nanofossils. What I want to point out is the black bars indicate different taxa when their first and last appearance are, and where the bar gets very, very thick, that is a specific zone for abundance, and when it gets very thin, that's a zone for when it becomes very rare. Sometimes it becomes abundant and then goes extinct, and sometimes it becomes rare and then becomes prolific again. We can use the overlapping ranges of these and describe when a group becomes abundant, when they become rare, when something appears, when something disappears, to help us constrain these various biozones that we can study and then link the stratigraphic units that they're encased in with one another. And really, this is what we base the old principle of faunal succession on. The idea that organisms in the fossil record exist for a finite period of time. Not every organism exists forever. We have organisms that are, they appear at some period of time and they go extinct later. Considering most organisms have a limited range in the geologic record, we use their presence and absence in respect to one another to help us describe relative ages from one unit to the next. So sedimentary rock strata observed to contain certain types of fossilized plants and animals can be used to then correlate those over long distances. So in this case, let's look at the age of rock unit A. It possesses that green ginkgo leaf. It possesses a couple of vertebrate skulls and the maple leaf. Now, the other fossils that you see passing through it, like the clamshell or the brachiopod, those are present in both units. Same thing with the starfish. So it's not really that useful. However, notice what units we only have these. Rock unit B is the only time you'll see a starfish, for example, a brachiopod, a ginkgo, a clam, and a trilobite all together at once. Rock unit A, you'll see the clam, the ginkgo, the 2 skulls, the maple leaf, the brachiopod, and the starfish together. So this is why we usually need multiple taxa to help us do proper faunal succession. Now, we define a group or single layer of strata that contains the same major fossil assemblages as a stage. So how do we define a stage? Really, it comes down to what's going on at their boundaries. When we get to a boundary of a stage, it's defined by intervals where we have the last appearance, either there's a disappearance or a significant decrease of these distinctive assemblages of life forms, coupled with the replacement in the rock record by something else. So at the end of the Ordovician, we lose a whole bunch of organisms, and that also marks the beginning of the Silurian because we have them replaced by a Silurian fauna. Furthermore, we can also describe zones, which are smaller scale units that are defined primarily by that stratigraphic ranges of the species that we have in those rocks, regardless of the lithology. So you might have the same species present in different rock types, and that's telling you that you're in a zone of equivalent time, maybe not necessarily the same facies, thus environment. Each of our zones that we look at are characterized by the presence of numerous species that we don't see in units above or below, regardless of the rock type. The best biostratigraphic markers would be index fossils, or also known as index species. And these are going to be very unique or ubiquitous forms of life that we see present during very limited periods of geologic time. If you have an organism that's in the fossil record for hundreds of millions of years, virtually unchanged, it's not going to be a useful biostratigraphic marker. It's not a useful index fossil, because if you find that fossil in a rock, it doesn't tell you very much about when that organism was alive, because it's present throughout a significant portion of the time period. Similarly, we want our index fossils to be easy to identify, abundant, and widespread. It's not useful if they are hard to differentiate from others, if they're only found in one place, or if they're rare. So usually our index fossils are microfossils because they're small, they're widespread, they have a global distribution in many cases, and they're in some cases very unique. So we use our index fossils, though, as guides to understand the age of rocks that they're preserved in. And every geologic period has at least a handful of well-defined and well-understood index fossils. The biogeographic province is defined as an area within one of these zones that we define by the geographic limitations, beyond which we can't trace that zone. So in other words, what is the distribution of this particular group of organisms? Is it local or is it global? For index fossils, it's good if they're global, though sometimes local ones do have their uses. Here are some of the more common or well-known index fossils for our different geologic periods and different eras. For example, if you find a rock that has the trilobite Paradoxites pinus, you're pretty sure it's from the Cambrian. If you find a rock that has Scaphites hippocrepus, that ammonite, you are pretty sure it's a Cretaceous age rock. And pectin gibbous, for example, would be a Quaternary pectin or scallop. So you can see there's usually more than one. I do want to point out that a lot of these are going to be invertebrates if they're not microfossils, and that's because, again, widespread, easy to find, and easy to tell apart from one to the other. So how do we actually break down the differences of our biozones? Well, we have a couple of different types of biozones that we can describe. Again, these are all based on ranges of organisms in the geologic record. A taxon-range biozone, which is here in figure A, is going to be based on the total range of one organism, its first and last appearance. So every fossil organism has a range, a taxon-range biozone, its beginning and its end. And this by itself, unless it's a very unique index fossil, isn't entirely useful by itself. We have to use this coupled with other types of biozones to help us constrain age. A concurrent range biozone, which you can see in figure B, is based on the concurrent occurrence of two taxa, specifically the time in between two taxa first and last appearance. So in this case, you can see that our first bar in figure B kind of comes to an extinction event, or its last appearance is at the top of that box, and our second one has its first appearance at the bottom of the box. The range of their overlap is what we would call the concurrent range biozone. Figure C shows an interval biozone. This is the time in between the first appearance of two taxa. So this is what we call the lowest occurrence of taxa. So this is where we had species 1 and species 2. When did species 1 first appear? When did species 2 first appear? The time in between. So it's almost like the only time when species 1 is by itself. Related to that, but alternatively, is in figure D, where we have our interval biozone for the highest occurrence of taxa. In this case, the time in between their last appearance. So when one goes extinct until the next one goes extinct. A lineage biozone is a little bit more complicated. This involves the successive species in a segment of evolutionary lineage. So you have to understand the speciation and the lineage of these groups. This is particularly useful when you're looking at things like microfossils, where you can understand maybe if they're relatively more recent and you can actually get their modern biological genetic range and understand their lineage. You can see when one speciated to when the next one appeared. So this one actually involves understanding some phylogenetics. F would be an assemblage biozone. So this is overlapping ranges of an assemblage and their co-occurring taxa. This kind of includes everything other than lineage biozone, which we don't use too often. But assemblage biozones kind of bring in interval, concurrent, and taxon range all together. And our abundance biozones, which you can see in figure G, this is illustrated usually as a thickened line, and it indicates a time when we have increased abundance of a particular taxa. Now, these we have to be a little careful with because they could be local. You could have a local population of an organism that just does really, really well and becomes abundant. It does not necessarily mean that it is going to be indicative of an abundance biozone globally. And this is kind of illustrating why we should be cautious about abundant zones, or sometimes called acme zones. You can see here's three species, species A, B, and C. And in this case, we're not using bold lines. We're using a shift to the right to show increase in relative abundance. Now, species A has a relative abundance early, species B later, and species C has an abundance zone later than the other two. So we have to keep in mind that this type of correlation needs to be done with some caution, because you can have maximum abundance at different times and at different localities. Again, this may not always indicate a global increase in abundance and success of a particular organism. But ultimately, the goal here is to do biocorrelation, where we can link lithostratigraphic units based on their fossil content. Now, sometimes this happens without using the same rock unit, but if we are dealing with the same rock unit, and we're usually doing this over more localized sections, we can link together individual units based on their fossil content. And really, this is the stuff William Smith was doing in England when he was putting together his geologic map. So you can see we have column A and column B with very different types of faunas distributed, but we can correlate them across and actually figure out the cross-cutting relationships of these units in between simply by correlating them based on their fossil content. However, we can actually show this in a little bit more of a complicated visual scheme to show how we can correlate two sections together based entirely on taxon range and interval range biozones. So for example, if you look down here at zone 1, where we have fossil species A, or taxa A, and this is a taxon range biozone. We see the first and last appearance of A, but notice that in section Y, this particular zone where we have this particular fossil is a little bit thicker, okay, than it is over in section X. When we move up our ladder a little bit, I want to point out zone 3. Okay. Zone 3 is based on predominantly species B. But notice that species B is present in 3 and 4. What separates zone 3 from zone 4 is the fact that zone 4 also includes C. So zone 3 is when we only have taxon B. We don't have A and we don't have C. And in between 3 and 1, we have zone 2, which is when we have neither B nor A. So now we've used interval, we've used some overlap, and we've used total taxon range biozones to build the first 4 units of these 2 columns and correlate them together. Notice with zone 5, we're looking at when we just have taxon C in both units without B. Jumping up a bit, we do the same thing with zone 7. This is when we only have D. Zone 8 is the combination of D and E. 9 is when we have E but not D. And then we can go back down and say zone 6 is when we have neither C nor D. And finally, zone 10 is the overlap of species F and species E in both sections. So we used interval and we used taxon range biozones to produce these zones. And this says nothing at all about the lithology at these 2 sections. However, notice the differences in the thicknesses from section X and section Y for our different zones. The zones are telling us time, and the time is about as accurate as the endurance of these organisms in the fossil record. Now, another way that we can use fossils with biostratigraphy, or to tell us something about stratigraphic history of a region, is by the biology of that particular organism itself and how the biology is reflected within the stratigraphic record. For example, let's take a look at the foraminifera Globirotalia truncatulinoides. Now, one of the unique things about Globirotalia, or this particular species, is that the species will coil itself during growth depending on the type of water temperature that it's growing in. So, for example, during cold water periods, we notice that in spiral view, this particular foraminifera rotates in a left, shall we say, left coiling pattern. And during warm periods, we see a right coiling pattern. But that would be in the umbilical view. In the spiral view, we see the opposite. So we have to know what view we're looking at. But they rotate differently or coil differently depending on the temperature. We can then look at a sequence of sediment cores taken from, let's say, the Atlantic Ocean, these 3 coring stations, and we can see that during or in our record for core number 1, just off the eastern shore of South America, we can identify, here's our 50-50 line right down the middle, and we can see when we have periods of right-handed coiling versus left-handed coiling in abundance. And then we can compare that to our other units. And what do we notice when we put all these together is we have events where we see similar types of spikes. And that's telling us something about global sea surface temperatures, since these are foraminifera that live in the oceans and they're affected by water temperature. So we can look down in the record and see how temperatures have been different based on the fossils and how those fossils grow when they were alive. By comparing numerous cores and the fossils within them, that have been correlated across, we can actually start to learn something about how quickly sediment accumulates in one location to another during the same interval of time. Remember that if you have your first appearance data and your last appearance data, those are usually corresponding across correlations from one unit or from one column to the next. So let's say we have two sections. We have section X and we have section Y. And we have 9 species in each one. And we're looking at the total range zones for species 1 through 9 in both of these sections. And we have the distance above base in meters. Okay. We can take section X and make it our x-axis, and section Y and make it our y-axis, respectively. And we can correlate, for example, where we have the first and last appearance datum of species 1 using section X as your x-axis and section Y as your y-axis. We can correlate those across, where in this case our circles are going to indicate the bases or our first appearance, and our diamonds are going to be the top of the range or our last appearance datum. And then we can put all of those together and we can draw a line of best fit through them. And in this case, it's a 45-degree line, which means that these two units are accumulating sediment at about the same range, because the thicknesses, or the depth, is about the same for the tops and the bottoms of the first and last appearance, respectively. Here's another way of looking at it. Let's focus on this little trilobite here. And this is in one column, and this one is in another one. So here's our trilobite from column Y, and here's our trilobite from column X. And we've actually turned our columns side by side. We know we can correlate them straight across, but we're going to correlate them perpendicular to each other. Here's the first appearance of trilobites in column X, and here's the first appearance of trilobites in column Y. Now let's look at the last appearance of trilobites in Y and the last appearance of trilobites in X. We don't have to label them on our plot, but it gives us points of which we can draw our line of correlation and actually compare these. And in so far, the two examples I've provided, it's been fairly simple, and we're looking at approximately 45-degree angles, so pretty much equal sedimentation, more or less, from one unit to the next, but it doesn't always work that simply. Because with graphical correlation, once we plot all of our first and last appearance datum from two sections, we look at the best line of correlation, and it may not always be a single line. In this case, we have a two-part line, which starts out being a little bit faster in section 1, and then switches to being faster in section 2 and slower in section 1. Similarly, we start out in our second example with a line that is pretty even between our first two sections, and then we see it pretty much stop in section 2 and only increase in section 1. So we have a plateau indicating a hiatus in one of our sections. And then it continues more or less equal on both sides. So this could have been a localized hiatus where you stop sedimentation in one spot and not the other. And if we can apply some radiometric dates to these, we can actually figure out how long that hiatus actually took. We all know that isotopes are very useful for determining absolute ages of the Earth, but stable isotopes can also be very useful for relative age dating and correlation. Our stable isotopes are ones that aren't going to be breaking down, so they're not going to be used for radiometric dating, but things like oxygen 16, oxygen 18, comparisons with carbon 13 and carbon 12, sulfur 32, 33, 34, and 36, and strontium 84, 86, 87, and 88 can all really help us out a lot with trying to figure out changes in various Earth systems and also correlating units across large distances and local ones as well. Oxygen isotope fractionation is a good example of this. Water, of course, is H2O. And some of the oxygen in our water molecules is a little different than most of it. Most of the oxygen that we see in our water is oxygen 16. It's regular elemental oxygen. Our oxygen 16 will preferably evaporate. So water that has oxygen 16 will evaporate, precipitate, and during warm events return back to the oceans, keeping our oxygen 18 isotopes kind of lower. However, during cold conditions, water evaporates, it precipitates out, and the oxygen 16 gets stored in the form of ice and glaciers on the continent. This slightly enriches our seawater with water that has oxygen 18. Meaning any organisms that are building calcium carbonate shells during those times are going to reflect this fractionation difference and thus be stored in the geologic record. So during a non-glacial period, seawater with uniform oxygen isotope ratios return right back to the ocean. 16 gets evaporated, gets rained out, returns to the ocean. During glacial periods, 16 is evaporated, it's precipitated out, and it stays on land or in the form of glaciers, enriching our seawater with oxygen 18. And you can look at this by going and checking out ice sheets and finding that they are predominantly made of water with oxygen 16. We don't evaporate oxygen 18 quite the same. And indeed, when we look at shifts in what's going on with oxygen isotopes in the Arctic and Antarctica, we can see when we have major shifts in those oxygen 18 isotopes, especially if we're looking at this in concentrations of per mil. So we're not talking about a huge amount of oxygen 18 concentration, but enough that it is definitely detectable. So when we compare records from the north and southern hemispheres and see that during the same period of time we have the same shift in oxygen isotopes, that tells us global climate change. However, happens in a lot of times it's just a local event. So sometimes we have local climate change and other times it's global, and we can use sea ice and in some cases microorganisms that are fossilized from both hemispheres to help us differentiate whether we're seeing a global change in climate or a local one. So we can put this all together and actually compare using the delta or change of oxygen 18 from benthic bottom-dwelling foraminifera, looking at the amount of oxygen 18 in their shells. We can put this together and actually get a record of concentrations of sea ice versus open sea over the last 450,000 years. So for example, if we start from our more modern times and work our way back, here's our last glacial maximum. You can see that's when we have a lot of sea ice. And then if we go back about 150,000 years, we actually had a warming period. And then we went, before that, we had ice. So we can kind of point out these major shifts and see that we had a very cold period, then it went warm, then cold, warm, cold, warm, cold, warm, cold, going into our modern day interglacial Holocene. Again, just looking over the last 150,000 years before present, our full glaciation here, and this is when we have the termination of glaciation, and we start seeing a lot of our isotopic changes and sea level changes as we start going into warmer periods. This is our sea level rise, and then we start seeing it fall again as glaciation is starting to cover. And then we get into our Holocene today, full interglacial with very high sea levels. Again, this is based on the per mil deviations from the standard mean ocean water for oxygen 18. The more negative you get with oxygen 18, that's the warmer it's going to be. Now, before we jump onto radioactive isotopes, let's talk a little bit about magnetostratigraphy. This is another way of calibrating the geologic time scale based on changes in the Earth's magnetic field, specifically the polarity. There are times when Earth's magnetic north and geographic north are more or less aligned, and there's times when they are literally polar opposites to each other. This is going to be imprinted on rocks that we can then look at and find how these units all correlate together. The Curie point is really important here. This is the critical temperature between about 500 and 600 degrees Celsius, especially for magnetite. Anything above this and we remelt everything again. So this is a really important temperature to lock in Earth's remnant magnetism. So these are going to be for iron-bearing minerals that will become magnetized at this temperature and will then indicate and be affected by the Earth's magnetic field. So this would be the equivalent of if you wanted to make a compass, you could take a small petri dish of water and put a cork in it and put a needle, a metal needle, into that cork. Now by itself it's not going to do anything, but if you magnetize that needle, it will respond to Earth's magnetic field, and that's how you can essentially make a compass. It has to be magnetized, and the Curie point is when we are actually magnetizing our material. Once we get cooling going on, the magnetite molecules will keep that orientation locked in place unless they're heated past that Curie point again. So any mineral that is enriched with iron can potentially do this. We call this phenomenon thermal remnant magnetism. Essentially, it means the Earth's magnetic field is imprinted on these iron-rich rocks during cooling. And it'll stay that way unless they're reheated up past 500 to 600 degrees. Now, so far that's dealing predominantly with igneous rocks, as we're talking about rocks melting and cooling. But you can do this sometimes with sedimentary rocks. It's called detrital remnant magnetism. In this case, we're looking at the preferred orientation of lots of sedimentary particles that happen to be magnetic. So if a mineral is already magnetic or magnetized, and as, let's say, that grain of silt that is iron-rich is falling through the water column, it will orient itself in relation to Earth's magnetic field, and then when it is settled, it gets kind of locked in that position. Is it as reliable as using igneous rocks? It's pretty good. It works fairly well. It's enough to give you a rough idea and then compare it to other rocks, but it isn't quite as a crisp method of determining magnetism as using igneous rocks. So again, small magnetic minerals like silts and clays that are rich in iron and that are magnetic already will rotate as they're falling through the water column and depositing. And then they just align themselves with the magnetic field. So what you want to do is mark current magnetic north on your rock sample before you collect it. You don't want to use something just laying on the surface. And then you're going to be comparing what is the magnetic signature in that rock compared to what is the orientation of magnetic north when that rock sample was taken. So we can develop these kind of geomagnetic polarity timescales like this, in this case looking over the last 500 million years. And you can see we can base this down on individual samples and see, okay, this is a period of time where we have normal polarity, and anywhere it's white is going to be a reversal. And so it's almost like tree ring analysis or dendrochronology. You're looking at the distinct patterns of bands of a thick normal polarity versus an inverted polarity. And when you can constrain a certain pattern, you can then give it a polarity epoch name like the Gilbert, the Gauss, the Maruyama, or the Bruns. And of course, if you can radiometrically date these rocks as well, then you can get absolute ages for how many millions of years it took for us to go from a normal to a reverse polarity and back and forth again. So we can actually learn all about our ocean crust and how seafloor spreading actually works thanks to thermal remnant magnetism and radiometric dating. Which of course brings us to how we calibrate the geologic timescale with radiochronology or radiometric dating. This is looking at ages in years before presence for rocks and thus events in between them. This is giving us an absolute age. Now I'm not going to suddenly turn this course into a isotopic geochemistry course, but I do want to cover the basics of how we use radiochronology. Really, it involves looking at radioactive parent elements or isotopes and their radiogenic daughter isotopes. So for example, uranium-238 to lead-206. Imagine a set of screwdrivers. Each one is a little bit of a different size. To do the right job, you need the right tool. And so we have a whole bunch of different radioactive parent-daughter isotope pairs with different time ranges associated with them that we can use to help us date rocks and calibrate that geologic timescale. The basic equation for calculating radiometric age is time is 1 over lambda times the natural log of the difference between our daughter elements over our total number of isotopes plus 1. What am I talking about? Well, N is the number of your parent atoms. When an igneous rock, usually, cools and crystallizes and the minerals form, the clock starts ticking. from parent radioactive materials, radioactive isotopes, to stable daughter forms. N is the number of parent atoms that you have. Ln, of course, is the natural log of base E. D is your total number of daughter atoms. However, sometimes when a rock forms or a mineral forms, some daughter atoms are already present, and they didn't form from radiometric decay. That's D0. This is the number of original daughter atoms. And if we really want to understand how radiometric dating is working, we have to know the difference between how many daughter atoms we start with and how many daughter atoms we produce from parent atoms decaying. Lambda is a decay constant, and that decay constant is calculated a little bit different for every single pair of isotopes we're looking at. It's always 0.693 over the half-life of that radioactive element. Now, depending on the job that you want to do, you have a wide variety of different isotope pairs to work with. If your material is really anything under 40,000 years old, you can use carbon dating, which is looking at the breakdown of carbon-14 to stable nitrogen-14 with a half-life of about 5,730 years. Now remember, a half-life is the time it takes to break down half of the parent isotopes into daughter isotopes. Another good one to use would be thorium-230 to radium-226. This has a half-life of 72,200 years, and it's really useful for anything that's a little bit under 250,000 years. Uranium-238, lead-206 has a half-life of 4.5 billion years, or 4,500 million. And this is going to be useful for anything from about 4.5 billion to about a billion and onward. Also, keep in mind the types of materials that we need to date these. Uranium-238, for example, to lead-206, anything that's going to have potential uranium in it, so zircons, monzonite, sphene, uranium and thorium minerals. Uranium-238 to some what we call spontaneous fission tracks. This is where we can start using zircons, volcanic glass, apatite, and so on. You can see zircons, muscovites, feldspars, and micas are really, really, really common to use in radiometric dating. Now, of course, I want to point out that not all rocks are useful equally for radiometric dating. Volcanic rocks are great. Ash falls and lava flows. These can be contemporaneously embedded with sedimentary rocks. You can have a sedimentary rock deposited with an ash layer instantly deposited on top of it, and that's great. That can give you actual ages of sedimentary rocks and a very, very close proximity to those volcanic layers. Plutonic igneous rocks, like your granites and so on, these will give a minimum age for the rocks that they're intruding. Sometimes if they lie unconformably beneath our sedimentary rocks, they'll give a maximum age for the overlying sedimentary rocks. So again, there's a little bit of constraining needed there. Metamorphosed sedimentary rocks are interesting because we're really looking for materials and minerals that are forming during metamorphism. So ultimately, these are giving minimum ages for when those rocks became metamorphosed or when the non-metamorphosed rocks were ultimately deposited. Sedimentary rocks are tricky. If you grab a random sandstone and grab a piece of quartz out of it or something, or maybe it's an arkose and you grab a chunk of feldspar, it's not going to give you the age of that deposit. It's going to give you the age of the feldspar that is in that deposit. It's going to give you the age of its host rock, which is probably a granite, billions of years older. However, sometimes we can use things like materials in those sedimentary rocks, like fossils or wood, if it's relatively young, and we can do carbon dating on that, but once you're past 40,000 years, it doesn't really matter. However, there are some minerals that will form autogenically in a sedimentary deposit, so glauconite and zircons, and we can actually get a minimum age for those sedimentary rocks from there. So it's a lot of combining radiometric techniques and our relative age dating techniques, usually to date sedimentary beds. And again, to remind you, half-life is the time it takes to decay half of the parent atoms and thus grow half of our daughter atoms. So if we look at a diagram like this, where we have time 0, that's when that rock forms. That's when that ash is erupted and is deposited. At time 0, that's 100% parent material. We haven't broken down anything to produce daughter elements yet, minus what may have already been there. After the first half-life, we're now down to 50% of both. We've lost 50% of our parent atoms. The second half-life, we now have 25% parent remaining, and we have 75% daughter, and so on. So by the time you get to your fifth half-life, you only have about 3.12% of your parent atoms remaining. After that, it gets to be kind of hard to detect them. Now, we mentioned before that sometimes we do already have daughter isotopes or daughter elements present in the sample that did not come from radioactive decay. How do we figure that out? What you'd normally do is when you take your rock sample and you send it out to the lab, you have them detect the number of parent atoms and the number of daughter atoms and find a ratio of that. And you have them do it for a couple of samples and you get the numbers for those. And you simply put them on one of these isochron diagrams, like a blank version of this, where you have your daughter going up the y-axis and your parent going across the x-axis. And you plot them and you look for a line of correlation, and wherever they meet up on the daughter atom ratio portion, that's your D0. So in this sample, hypothetical sample, the daughter atom ratio would have been 0.2. So that's what we would be subtracting from our detected daughter then in the sample that we're trying to date. So it's just a correction, so we don't have to always assume that when an igneous rock forms, there's absolutely no daughter elements present to begin with. So I'm sure some of your heads are kind of spinning right now with all of this. So let's actually walk through an example, a real-life example. This is an outcrop or a cross-section of the Little Rocky Mountains in the northern portion of Yellowstone National Park. We have a syenite porphyry that has uplifted its way and pushed up all of the overlying rocks sitting on top of it. When did this intrusion occur? At least when did it start? Because that's the best thing that we can figure out. When did the resulting uplift occur? Well, we take a sample of this syenite and we find the uranium-bearing mineral uraninite inside of it. That's great. Uranium is important because now we can do uranium-235 lead-207 dating. Okay, so not all of the uranium in that uraninite is going to be U-235, and we are presumably going to have some lead-207 already in there before any decay occurred, but we are going to have some atoms of U-235, and we can correct and figure out by looking at a number of samples and using that isochron diagram how much lead-207 we had to begin with. So we take our sample, and we're going to do uranium-235 dating to it. And remember, uranium-235 to lead-207 has a half-life of 713 million years. That's the time it takes to break down half uranium-235 and turn it into lead-207. We send our sample out to the lab. They analyze the rock for us chemically, and what do we get back? We get back a number of daughter elements, a ratio of 0.25. We get an N value of 1.000012, so 1 essentially. So that's the parent material remaining. And they determined D0 to be 0.3. Remember, that's the ratio of daughter elements that were present before decay. The first step is going to be to calculate our decay constant, which you remember is is defined as lambda, which is 0.693 divided by the half-life, which in this case is 713 million. That gives us a decay constant of 9.72 times 10 to the negative 10. Okay, so we have our decay constant. Part 2, plug and chug. We're going to look at our equation. We already know that decay constant is going to be 9.72 times 10 to the negative 10. We have our D0, we have our D, we have our N. We know how to push the button for natural log, so we can go ahead and calculate this. So time is going to equal 1 over our decay constant, 9.72 times 10 to the negative 10. That value will then be multiplied by the natural log of d0 minus d. So how much daughter elements did we have before decay versus right now? So 0.3 minus 0.25 over our total number of parent atoms, which is 1. We take that value, add it to 1, and we get the natural log of that. We calculate this all together, and we get approximately 50.2 million years is the age for this uplift. And that makes sense. If we look at the overlying units, we have Jurassic and Cretaceous units above that. Those are the Judith River we're looking at around mid to late Cretaceous. So this happened much after. This happened about 50.2 million years ago for the age of this uplift. So this equation looks really intimidating, but if you have the D value and DO, you know how much daughter elements you have, and you know the proportion to what was caused from decay versus what was caused from just already in there. And you also know the number of parent atoms. You know the half-life. You can actually calculate how old one of these rocks are. And finally, we can put it all together. We can date igneous rocks like an igneous dike at about 1.25 million years old. We have a batholith underneath all of it that's 135 million years old. And we can then get a constraint for what's the time for the sedimentary units in between. Now think back to the biostratigraphy stuff we talked about with the graphic correlation. Imagine if in some of those units we had an ash boundary. We could radiometrically date some of those unconformities and figure out not only the age in which these fossils were, their radiometric ages, but also we can calculate how much sediment was accumulating over an actual known numerical amount of time. So we can bracket sedimentary units between two igneous bodies. We can also bracket sedimentary units between metamorphism and igneous units. And any fossils that are encased in there too, we can now put an actual age calibration onto our relative ages from biostratigraphy. So we can put all of this together. We've already discussed how magnetostratigraphy is also played in with radiometric dating. So all of these factors can all come together, and this is how we ultimately can calibrate and constrain our geologic timescale. Now for next week, we are going to be looking at Chapter 8, Basin Analysis, and kind of tying all of this together, everything we've looked at with vertical dimension, horizontal dimension, and now time dimension. We're also going to be taking a little bit of a look at Chapter 9, looking at sedimentary stratigraphic systems, where we'll look at some of the large-scale global cycles that we can identify in our basins. So we will see you next time.